Hi, my name is Daniele Bailo. I'm a computer scientist and an engineer, now leading the technical developments of the EPOS research infrastructure in the domain of solid earth sciences. On behalf of our IT team, I'm here to show you how existing interoperable building blocks can be used to enhance functionalities of research infrastructures. In the new science era, data and service provision is often carried out by research infrastructure, that is to say, dedicated infrastructures for research that provide resources as datasets and processing or visualization tools for scientific data, often from a specific domain. Similarly, virtual research environments are dedicated to research, but their focus is on the aggregation of different resources and tools from several research infrastructures, together with other useful tools for research, as communication tools, enhanced discovery or visualization software, and advanced services, for instance, authentication services. In this scenario, the general objective for the student in this lecture is to learn how research infrastructure can be enhanced by using interoperable components or building blocks from existing virtual research environments. As an example, we will discuss the use case of EPOS and VRE4AC. The Directorate General for Research of the European Commission defines a research infrastructure as any facilities, resources, and related services that are used by the scientific community to conduct top-level research. As knowledge-based resources such as collections, archives, or structures for scientific information, so for instance datasets, something that can be single-sided or distributed. Examples of research infrastructures according to these definitions are particle accelerators, as the well-known Large Hadron Collider, but also simpler research infrastructures like an institutional database providing access to experimental data in an open access way. The EPOS research infrastructure will be used as an example to illustrate this. So let's now start the lecture. We mentioned the research infrastructures. We will now look into this matter by examining the EPOS use case. EPOS acronym stands for European Plate Observing System. Many institutional data providers in the field of solid earth science exist in Europe, and they provide access to datasets and other resources at national level. However, only some of them are federated and integrated, and as a result, a user willing to make use of resources, that is to say datasets, data products, software or services, has to access institutional portals, department database, and other scattered resources of information. That's where EPOS comes into action. Its main goal is to integrate scattered resources across Europe in the field of solid earth sciences. That's why EPOS is also referred to as a long-term plan for the integration of research infrastructures for solid earth science in Europe, with the goal of investigating tectonic processes, earthquakes-related phenomena, volcanic eruptions, surface dynamics, and georesources. Research infrastructures and facilities encompassed by EPOS are located in 25 countries, mostly European countries. They also include international organizations like Orpheus and the EMSC in seismology, Intermagnet in magnetic observation discipline, EuroGeoSurvey in geology, and others. The amount of resources to be integrated is huge, thus making the challenge of building EPOS exciting. We want indeed to integrate more than 250 national and regional research infrastructure, provide access to data produced by around 10,000 sensors in Europe, manage and give access to several petabytes of data. Thousands of users are expected, so EPOS also needs a robust user management system. Summarizing, EPOS is a distributed research infrastructure that integrates existing and future advanced European facilities and regional research infrastructures. It also takes advantage of new e-science opportunities provided by other European stakeholders. For instance, just to mention a few, infrastructure providers like EGI and UDAT, VRE developers as VRE for IC, and other initiatives as AARC2, EMVRE, and others. Let's now have a look at what users can do with EPOS. What we show here is a work in progress that will be soon released to the scientific community. EPOS web application is a map-based application which enables scientists to search for desired resources by using spatiotemporal coordinates, filtering keywords and tags, and selection by domain together with a simple free text search. In the example, a user searches for earthquakes. On the bottom of the screen, a list of matching resources is provided in a tabular way. In this example, it includes organization, persons, and services. As shown in the map, resources are spread across Europe. This is the integration action EPOS is now carrying out, and which constitutes the main added value of any interdisciplinary research infrastructure. Users can indeed have a single point of access instead of connecting to many portals, using multiple username-password pairs, or, as sometimes happen, managing data transfers by sending files via email. Data access services that matches the search criteria can be configured. In practice, through a simple web form, the user can select the desired slice of data. The configuration is then added in a personal workspace. The workspace concept is close to the concept of shopping cart we are used to when doing online shopping on Amazon or similar portals. It is the place where users add all resources of interest, in this case datasets, services, persons, organization, and so on. When resources are services that provide georeferenced data, they can be selected for visualization on a map, as in the case of the map of historical earthquakes. Visualization on map is fundamental for solid earth sciences. The possibility of looking at datasets in a visual and integrated way is the first fundamental step to the integration. Solid earth scientists, indeed, often study specific phenomena in a given area and in a given time range. In order to unravel the processes triggered by natural events we usually call hazards, as for instance earthquakes and volcanic eruptions. Each of the visualized resources will also be available in the form of a downloadable file or waveform to be processed. But that's something that is now under study and implementation within the EPOS community. There is an incredible amount of opportunities created by such new e-science platforms, which enable multidisciplinary data and services to be used together, from a single discovery, search, processing, and visualization environment. That's the future we are building. Now that we have an idea of what EPOS distributed research infrastructure can do, let's examine what lies behind the scenes. Again, we will use the EPOS example. However, other multidisciplinary distributed research infrastructure build upon the same fundamental concepts. The diagram in the picture represents the organizational architecture at technical and governance level of EPOS, which, reading from left to right, is composed by the following assets. Thematic core services. They are discipline-oriented European nodes. They provide access to resources from specific domains like geodesy, volcanology, and so on. In practice, it means they aggregate data, metadata, services, and other resources from one discipline, doing a huge work on harmonization of data and metadata formats, and provide uniform access to the resources from a specific discipline. They also care about other aspects like data policy. Right in the middle, we find the heart of the EPOS project, that is to say, the so-called Integrated Core Services, or ICS. Their role is to integrate data, metadata, software, and services from the communities, in particular from the aforementioned thematic core services, and provide a uniform and simple access to end users to resources in the solid earth domain. This is done with a co-design approach, which brings together expertise from engineers, domain scientists, technical staff, both from the communities and the EPOS integrated services. In this way, we can build a system that satisfies user requirements and at the same time is technically leading edge and open to measure extension in case new technologies or new requirements comes in the future. In one word, it is tailored to users' need, but scalable and interoperable with other technologies. One of the main components of the integrated core services is the metadata catalog based on the Serif model. At this level, ICS staff has done an enormous work on metadata by enhancing the initial structure of the canonical Serif model in order to take into account all requirements from solid Earth communities. Even though willing to provide access to computational resources and scientific workflows, EPOS is not building a new supercomputer. What EPOS is doing is using external distributed resources. The keywords here are optimization of resources and interoperability. Optimization, because EPOS wants to leverage on and use existing software like modeling and visualization tools and hardware resources as HPC or other resources provided in the framework of the European Open Science Cloud. Interoperability, because such external distributed resources need to interoperate with the main system through well-defined standards and protocols. The last element of the architecture is the user base. EPOS intends to serve and be available for different categories of users: scientists, IT specialists, policymakers, and even the so-called citizen scientists, that is to say, to the society as a whole. This implies that different methods for accessing resources and different user interfaces will be built. At the moment, scientists are the priority target audience, followed by policymakers and IT specialists. This is the end of the first part of the video, where we discussed what research infrastructure are, what distributed research infrastructure like EPOS can provide to the users, and what their governmental and technical organization is. If you now want to discover how technically a research infrastructure like EPOS is built and how it can be enhanced by using existing VRE components, then we invite you to follow the second part of the lecture.